Okay, so hello everyone. My name is Anudh Mishra and I'm doing MBBS from AIIMS Bhuvneshwar right now. Today I'm going to discuss the chapter Metallurgy, General Principles and Processes of Isolation of Elements. So this chapter discusses how we extract elements in their pure form, how we refine them, how we process them, and we get a pure element, usually metals. The basic principles used in this chapter are thermodynamics, and you should know the basics of thermodynamics, like what is enthalpy, enthalpy change, negative enthalpy change, positive enthalpy change, entropy, entropy change, again negative and positive. Apart from that, you should also know Gibbs free energy and feasibility of a reaction. All those concepts will be of really help, right? So let's start. So what is a mineral? Okay, so mineral is a naturally occurring chemical substance in the earth's crust. Any naturally occurring chemical substance in the earth's crust, which we can obtain by mining. But what is ore? Ore is, see, ore is viable to extract the metal, any mineral from which you can extract the metal economically. Like it should not cost very much, it should be easy to extract. That mineral is known as ore. So, ore is a kind of mineral from which you can extract an element easily or in a viable method. Then ore contains a desirable substance. This is not true always. It contains contaminations known as gangue. Okay, they are called, the contaminations are called gangue. And we have to, this is what metallurgy is concerned with. You remove the gangue from the ore and you get the pure metal. Here we'll concentrate on the following steps. First is we will enrich the ore or concentrate the ore, then isolation of the metal from its concentrated ore, purification of the metal. These three steps are broadly studied under metallurgy. So let's see the occurrence of metals first. How do metals occur in the Earth's crust? Elements or metals and their ores are listed in this table. Okay. Aluminium is the most abundant metal and it is the third most abundant element in the Earth's crust. So the most abundant element in the Earth crust is oxygen, followed by carbon, then aluminium. Okay. So many gemstones are impure forms of alumina, and the impurities range from chromium in ruby and cobalt in sapphire. So if in Al2O3 you have an impurity of chromium, that will create ruby. And if the impurity is of cobalt, that will create sapphire. So these two are asked questions. Sometimes they ask these questions in match the following or something like that. So it's better to remember. Then we have some ores of some important metals. For example, the viable ore of aluminium is known as bauxite. Okay, and the formula they have given, it's not Al2O3 exactly, but it contains hydroxide also. Looks something like this. So it is variable. X is ranging between 0 to 1. Anyways, if anyone asks you what the formula of bauxite is, go with Al2O3. Okay, this is just a small info which might not be of use every time. Okay, so it's safe to say Al2O3 is bauxite, right? So let's move forward. Next, there is kaolinite. It is a form of clay and it has a definite formula. It has aluminium and silicon. The ones which I'm underlining or highlighting, they are the ones you tend to forget. So you take a screenshot of this after I'm done. Iron, hematite is Fe2O3. Everyone knows. See, magnetite, you get confused. It is Fe3O4. which is basically FeO plus Fe2O3. Then you have siderite. Again, you'll forget siderite, and iron pyrites is FeS2. Okay. Next, copper. Copper is occurring as copper pyrites. So you can see the similarity between iron pyrites and copper pyrites. In iron pyrites, there is no copper, but in copper pyrites, there is iron. Malachite, everyone knows. Cuprite, everyone knows. It is the, see, ite usually means an oxide ore. Okay. So if there is a suffix ite, it means oxide ore. For example, hematite, magnetite, cuprite, zincite. Okay. Copper glans, you might forget the Cu2S. Zinc blende is the most common form of zinc, also known as sphalerite. It is ZnS. Calamine is ZnCO3. Zincite is ZnO. Yeah, you may take a screenshot of this if you want. We'll move forward. So for the purpose of extraction, instead of kaolinite, we choose bauxite for aluminium. For iron, we use the ores which are abundant and do not produce polluting gases like SO2. See, if you burn iron pyrite, you will get SO2. Okay. Then for copper and zinc, any of the listed ores might be used. Now, we have obtained the ore from its source. We have brought it to the factory or wherever we are going to process it. So first step is going to concentrate the ore. So what does that mean? So actually ore is not consisting of the pure mineral only. It has mineral of our desire plus gangue. Gangue is the impurity in the ore. Both of them together make ore. So the process of removal of unwanted materials, sand, clays from the ore is known as concentration dressing benefaction. There are several processes, several steps, and it is based on the physical properties of the compound and of the gangue. So let us see some of the processes. The most important one is hydraulic washing. This is the most commonly used technique, although questions are not asked in this right now, but still it is based on differences in the gravities of ore and gangue, and it is also called gravity separation. So you can remember this. The lighter gangue particles are washed away and the heavier ones are left behind. Okay. Excuse me. Next is magnetic separation. Just as the name says, either the ore or the gangue should be magnetic. Then you can use a magnetic roller and separate this magnetic compound. Okay, the magnetic particles will get separated from the non-magnetic particles. So it is usually carried out in iron ores. Next is froth flotation method. This is the one where they ask you the most questions. So try to look at this important concept carefully. It is used for sulfide ores. Okay, I'm writing down, I'm underlining the important points. Okay. Firstly, you make a powdered ore and mix it with water. You add collectors and froth stabilizers. So what are the collectors? The collectors are the one which will collect the ore. They are pine oil, fatty acids, xanthates. Enhance the non-wettability of the mineral particles. Then there are froth stabilizers, cresols and anilines, which stabilize the froth formed by the collector. So first you mix the ore with water, add collector, you stir it. Okay. You stir it. What happens is the mineral particles are wet by oils while the gangue particles are wet by water. A paddle agitates the mixture, draws air, froth is formed, and froth carries the mineral particles and the oil. The froth is light because the oil is light, so it is skimmed off. It is then dried for the recovery of ore particles. So what happens? Different affinity of the ore at the gangue. So you wet the ore by oil and you wet the gangue by water, and you get A froth of oil, because it is light, so the froth of oil is accumulated on the top of water, and you collect it and remove the ore later. So the gangue stays in the water. Sometimes it is possible to separate two sulfide ores by addition of water and oil.
Recording in progress.
Okay, then we saw what depressants are. Okay, NaCN is depressant. And example. So this was your froth flotation method. They have shown an enlarged view of an air bubble showing mineral particles attached to it. See, this is an air bubble, and these are the mineral particles which you can see. Okay. All right. Then we have something called leaching. What it is a general term. It is used if the ore is soluble in some suitable solvent. So leaching is a chemical process. It is based on the solubility of the ore. First example of leaching is you leach alumina from bauxite. So you remove alumina or Al2O3 from the bauxite ore. Principal ore of aluminium bauxite usually contains SiO2 and iron oxides and titanium oxide as impurities. So three impurities you know: SiO2, iron oxide, and titanium oxide. You digest the powdered ore with concentrated solution of NaOH, high temperature and pressure. Al2O3 is converted to sodium aluminate, SiO2 as sodium silicate, leaving the impurities behind. And the equation which you need to remember is this. So look at how you have removed Al2O3 as sodium aluminate. Now, of course, you've removed some impurities, but how do you remove it from the sodium aluminate? So you neutralize it by passing CO2 gas, and Al2O3 is precipitated. At this stage, solution is seeded with freshly prepared samples of hydrated Al2O3, which induces the precipitation. So this is how you remove it from sodium aluminate. Sodium silicate remains in the solution, and the hydrated alumina is filtered, dried, and heated. So sodium silicate is left in the solution because you have not added anything to precipitate it. Now the hydrated alumina, you dry it, you get your solid alumina. This is how you do the leaching. Really important. Any of the steps could be asked. Okay. Other examples, like in the metallurgy of silver and gold, they use your forest reaction, and the solution of NaCl or KCl is used with air. What happens is, if suppose metal, you add it with NaCl and air, you get a cyanide of the metal. And how do you obtain the metal from the cyanide? Add zinc, it will form zinc cyanide, and metal will be freed. Okay, so you extract really rare metals by this forest reaction. This is known as forest reaction. Okay, guys. So done, we have completed how the concentration part of the ore. Let us now move on and see how do we extract the pure metal from its ore. So we are going to see half of it today, and we'll move to questions. The rest half, I think, we'll cover in the next session. Okay. Usually the sulfide ore is converted to oxide before its reduction. Oxides are easier to reduce. Thus, isolation of metals involves two steps: conversion to oxide, reduction of oxide to the metal. Now, any ore you convert it to oxide first and reduce the oxide. That is the method everyone follows. Okay. First is, how do you convert things to oxide? The first process which we are going to see is calcination. It involves heating when the volatile matter escapes, leaving behind the metal oxide. So you heat the thing as calcination. Like, calcination is usually done in absence of air. So you are doing it in absence of air. Any If any impurity is volatile, then to remove it, you'll use calcination. Suppose, first example, Fe2O3.xH2O. So H2O is an impurity, and if you can remove it as a volatile vapor, you do it by calcination. Similarly, heat ZnCO3, you get CO2 removed and you get the zinc oxide. CO2 is volatile, you do it by calcination. Similarly, calcium carbonate and magnesium carbonate, dolomite, you remove CO2, it is volatile, so you do it by calcination and you get the oxides of both the metals. So calcination is like typically for volatile matter which escapes, leaving behind metal oxide. What is roasting? Same, you heat the metal, but here you heat it in a regular supply of air. Okay, at a temperature below the melting point of the metal. This is usually done for sulfide ores. Okay, see, zinc sulfide, lead sulfide, copper sulfide, all heated in presence of oxygen will give a common thing called SO2 and an oxide, corresponding oxide. It is like sulfide ores of coppers are heated in a reverberatory furnace. This is a reverberatory furnace. Okay, here you keep adding air, and it has got a complicated structure. Keep adding air and keep pouring in the sulfide ore, converting it into oxide. Okay. Now, an important point is, if the ore contains iron, it is mixed with silica before heating. Why? Because iron oxide slags off as iron silicate and copper is produced in the form of copper matte, which contains COS and FeS. So what is happening is, if iron is an impurity in the ore, so how do you remove iron? You mix the ore with silica, heat it, because iron oxide will also be formed along with the corresponding oxide of the desired metal. You will get iron oxide also from this roasting. How do you remove that iron oxide? You add some silica, so it slags off with SiO2. Okay, and copper is produced in form of copper matte, which contains Cu2s and FeS. All right, so you remove iron oxide in this way. The SO2 which is produced is utilized for manufacture of H2SO4. This was the first thing, heating, like conversion to oxide, and you saw the two methods: either heating in absence of air if it matter is volatile, otherwise heating it in presence of air, roasting, which is done in a reverberatory furnace, usually for sulfide ores. Right. Okay. Next, reduction of oxide to the metals. See, it has got a complex. I'll show you the main reaction which is important to us. Where is it? Okay. We reached refining. Huh. Yeah, this chart is the important chart. If you need to remember how to, or at what temperature, or at what condition, or in what situation will an oxide get reduced to the corresponding metal, you need to remember, or you need to know the basics of this Gibbs energy versus temperature plot of the oxide. It is fondly called Ellingham diagram. Okay, so we will discuss Ellingham diagram, but before that, let us come to the basics of Ellingham diagram. Okay, so yeah, reduction of oxide to the metal, it involves heating it with some other substance acting as a reducing agent. Reducing agent combines with oxygen. So yeah, this is the metal oxide. You add a reducing agent, gives the metal, and the corresponding reducing agent turns into an oxide. So some are easy to reduce, some are difficult to reduce. Okay, depends on their thermodynamic property, temperature, all of them, Gibbs energy, all thermodynamic properties are a factor playing roles in reduction of metals. Now we'll see how this reduction of metals is, what it is based upon. Basically, thermodynamic properties of principles of metallurgy. We'll cover Ellingham diagram in the later section. So let's revise the basic thermodynamics required to understand the Ellingham diagram. First, this equation, relationship between Gibbs energy and entropy and your enthalpy. This, if delta G for any reaction is negative, then it is spontaneous. Okay. So we had seen conditions that if enthalpy change is negative, entropy change is positive, then delta G will be negative in all cases. So they are spontaneous at all temperatures. But usually for metals, it is seen that entropy change and enthalpy change are not negative and positive always. Sometimes the enthalpy change might be less negative, but the T delta S, the delta S might be really positive, which means entropy change would be very positive. So how do you proceed with the reaction at that time? How do you extract the metal? Because the metal tends to remain in its combined state. It does not want to be reduced. So at those situations, you increase the temperature. That's where the temperature comes into play. Metals like iron, aluminum, and all these reactive metals, usually they are reduced only at very high temperatures. So the T delta S thing becomes negative, too negative to support the delta H and create the overall negativity. Okay, so temperature is really important here. One more equation is there. It relates your standard Gibbs energy change with your equilibrium constant. We know a negative delta G implies a positive equilibrium constant. This can happen only when reaction proceeds towards product. Now, from these facts, some conclusions can be made. The value of delta G, if it is negative, then only the reaction will proceed. If delta S is positive, only on increasing the temperature, the value of T delta S would increase, and then delta G will become negative. Okay. Next, the reactants and products of two reactions are put together in a system. What will happen? The net delta G of the two possible reactions should be negative. Then only the reaction will occur. So what do they mean? I just showed you the basic principles of reduction. Now, there is a reducing agent which itself gets reduced to the oxidized to the metallic oxide while reducing the metal to its original form. So there are two reactions occurring simultaneously. One reaction which governs how the metal is reduced to its oxide. The other reaction how the reducing agent is converted to its oxide. Okay. So these two reactions will have their individual Gibbs energy change, but the overall sum of the Gibbs energy change should be negative. Okay. The net delta G of the two possible reactions, if it is negative, the overall reaction will occur. Okay. So you can couple the reaction, get the sum of the delta G, look for the magnitude, importantly the sign. Okay. There we come to before we come to the Ellingham curve, we'll just cover some examples. We'll do Ellingham curve in the next class. We'll move to some PYQs now after doing the examples. So see, reducing agent forms its oxide when the metal oxide is reduced. Now, role of reducing agent is to provide a negative delta G large enough to make the sum of delta G and the two reactions negative. So what happens usually, what is seen is uh, the delta G of metal oxide converting itself into metal is usually positive or very less negative. So it is not that feasible. So you add one more reaction. So this is C is basically some reducing agent. It converts into an oxide. Now this delta G should be a large negative value so that the total sum should be negative and large. That is what is the basic principle of metallurgy. So exploring different possibilities is what the metallurgists are concerned with, creating the best possible, best economical, best possible combination of reactions which will give rise to the free metal. Okay, yeah, they've given a similar example. This is a metal oxide reducing itself into the metal. The reducing agent takes away the oxygen. It can be visualized as the reverse oxidation of metal. So the delta G is written as this. Now reduction is being carried out. The reducing agent, its equation will be something like this. Okay, if the carbon is taken, so these two are reducing agents, either C or CO. Okay, either carbon solid or carbon monoxide. Now, if carbon is taken, there might also be a complete oxidation to CO2. They have given one more delta G. So these all these delta G are for the reducing agent reactions. Okay. Now subtract the equation from the first equation. You get these equations. If carbon is being used as the reducing agent, then this. If carbon monoxide is being used, and if carbon is getting converted to carbon dioxide, then this. So these three reactions have their own net delta G values. Okay, so they have their net delta G values. Then the difference in the two delta G. So this is what we've been discussing so far, that the delta G naught values for these reaction can be obtained by similar subtraction of the corresponding delta GF values. The next factor is temperature. Increasing temperature favors a negative value of delta G naught. So temperature is chosen such that the sum of the two delta G naught, the processes are negative. In delta G naught versus T plots or the Ellingham diagram, this is indicated by the point of intersection of the two curves. Okay. The difference in the two delta G naught values after that point determines whether reduction of oxide, the upper line, is feasible by the element represented by the lower line. If the difference is large, reduction is easier. All right. So we will start doing some PYQs now. I think like there will be very less questions from this part of the chapter, but anyways. Okay. Let's start with this. List 1, match it with list 2. Right now, we have not studied this one. We will move to the next question. A metal which is extracted by oxidation and subsequent reduction from its ore is. So, first you oxidize this metal and then reduce the oxidated metal. So, what they are implying is metal is present as either a sulfide, maybe. You oxidize it to metallic oxide and then you reduce it to the metal. Anything which you can find here? Yeah, it is copper, because copper is usually found as copper sulfide. And yeah, you extract it by oxidation and then reduction from it. So oxidation is done in what? reverberatory furnace. Then, which of the following reaction does not occur during extraction of copper? Let us see if we can solve this. First reaction, Cu2s plus oxygen, Cu2O plus SO2. Okay, I think this is roasting. Yeah. FeS plus oxygen gives FeO plus SO2. So yeah, for many of you might think that where does the iron come in copper? So yeah, copper usually exists as copper sulfide and iron sulfide. Just a second. अच्छा अच्छा କୋଉଠି କରିଛନ୍ତି ଠିକ ଅଛି ମୁଁ ନେଇଯିବି ମୁଁ ନେଇ ଆସିବି ଆସିବୁ ମୁଁ ନେଇଯିବି କୌଶିକ ବାବୁ ପାଖରେ most probably ତ ସେ ଦେବେନି most probably ତ ଦେବନି କାହିଁକି ସେ ନିଜେ ମାନେ ଚଲଉଛି ତାକୁ ଦେଖିବି ମୁଁ ପଚାରେ ଝିଅମାନେ ଆସିବେ ନା ହୁଁ 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 ଠିକ ଅଛି ମୁଁ ଦେଖୁଛି let's continue. So we were at, yeah, copper exists as both of these ores combined, or you can call it copper pyrites. You know what copper pyrites is, right? CuFeS2. So we had also discussed that in the extraction of copper in a reverberatory furnace during roasting, how do you remove iron? You had seen that, yeah, iron will also be converted to oxide and you can remove it by adding silica. So both of these reaction 1, 2 and 4 will be seen during roasting only. This is the slag formation reaction. Both of these. And but this reaction, I think it is not seen during copper extraction. Might be seen in some other reaction, but not during copper extraction. Next, in froth flotation method, a rotating paddle agitates the mixture to drive air out of it. Okay, so here we found this is wrong. It drives air into the mixture. So statement 1 is wrong. Statement 2 says iron pyrites are generally avoided for extraction of iron due to environmental reasons. Iron pyrites are FeS and they produce SO2 gas. So yeah, they are avoided because SO2 is toxic. So statement 1 is false, but statement 2 is true. Mond's process for refining, we have not covered it. Major component of which of the following ore is a sulfide based mineral? Okay, let's write out all the. So calamine is zinc carbonate. No sulfide is present. Siderite. Siderite is FeCO3. Sphalerite. Sphalerite is ZNS. Malachite is. So yeah, we have our answer. It is sphalerite or zinc blend. It is also called zinc blend. Next, in the extraction of copper, sulfide ore is heated in a reverberatory furnace after mixing with silica. Why? So you see, this is a direct NCERT question. That's why I ask you to read NCERT, read from NCERT also for JEE-Mains, because JEE-Mains asks NCERT questions directly like this. And if you have read NCERT properly, you'll answer them in a moment. Otherwise, you'll just keep thinking what will be the appropriate answer. Of course, you might be able to arrive at the correct answer, but usually if you are following NCERT diligently every time, you will your speed will increase. Okay, so that is very important in your entrance exams, how fast you're able to solve the questions, right? So yeah, let's go to the question. Why do you add silica? So we know it to remove FeO as FeSO3 or to slag the iron oxide that is formed from FeS present in the ore of copper. Next, refining we have not done. Then the methods not involved in concentration of ore: liquefaction, leaching, electrolysis, hydraulic washing, cross flotation. So electrolysis is not involved in concentration of ore. It is for refining. Liquefaction, yes. Hydraulic washing. Leaching, we have seen in bauxite. Hydraulic washing, liquefaction, both are same. Froth flotation we have seen in sulfide ores. One more method of concentration was magnetic separation. What do you think? Yes, ma'am. Yes, ma'am. Okay. So the correct option is AB. Oh, so they have removed liquefaction. See, you have to, if you get a dilemma like this, just select the most correct appropriate option. Okay. Here, according to them, they have removed liquefaction. So they have only added leaching, hydraulic washing, and froth flotation. So the answer is B, D, and E. So answer in the most appropriate terms. Okay, guys. Now, which of the following is incorrect? Well, we have not studied purification right now. We'll move to the next question. Assertion says in AIIMS diagram, oxidation of carbon. AIIMS diagram we have not completed. Okay, number of the following present in copper matte. So copper matte, you will get copper sulfide, copper oxide. See, you will get copper sulfide, copper oxide, iron oxide. Carbonate you won't get. So yeah, three: copper sulfide, copper oxide, and iron oxide. Because if you remember what copper matte is, after doing things, putting the copper sulfide in reverberatory furnace, you get copper matte. Copper matte consists of mainly these two, but some Cu2s might be also present. There is no chance of copper carbonate. Okay, so we have remove it. Next, reverberatory furnace, we have done this. Okay, the process that involves removal of sulfur from the ores. So smelting, roasting, leaching, refining, of course, it is the most appropriate answer is roasting here. What happened? I'll give you an example of roasting. PB, yes, it was used to remove sulfide and convert it to oxide. Okay, so PBS plus 2 PBO plus SO, right? And it is done in a reverberatory furnace. Next question says, which of the following reduction cannot be carried out with coke? We will solve this later. Doing Ellingham. One more Ellingham diagram. Next, yeah, overall question. So hematite, formula of hematite is Fe2O3. Formula for bauxite is alumina and variable number of H2. Okay, you can get multiple, formula for bauxite. So always see the most appropriate one. Here you don't see any other bauxite for aluminum formula, so go with this. Magnetite, I told you, Fe3O4, which is basically FeO plus Fe2O3. Malachite, the copper ore, copper carbonate and copper hydroxide. So one cut, two peak, one Silka four Nika. So this is fourth option is the correct option. Extraction of aluminum. We have not done this yet. Then match list one refining, not yet completed. So yeah, we are done. Okay, we are done with the topic. I'll just do a quick revision. Basically, we've seen process of like extraction of ore from concentration of ore. We have not covered extraction properly. So what is an ore? Minerals in which metals are present and from which their exact extraction is commercially feasible. Impurities are there, removal of impurities, concentration steps are there. So usually the metal compounds are reduced to the metal and thermodynamic and electrochemical concepts are given consideration. We have seen Gibbs energy change. It should be net Gibbs energy change should be negative, which becomes more negative on raising the temperature. So we had seen both these factors, total negative Gibbs energy change and effect of temperature on decreasing or making it more negative. So try to consolidate all the topics, try to revise the extraction processes, try to go and revise the concentration steps. Tomorrow, next in the next session, we will complete the Ellingham diagram and extraction, reduction and refining of the metals. So yeah, there you go. We are almost done with the session. Yeah, and I if you ask me for some advice for your JEE-Main, like it is like less than a month left now, I think I would advise you to keep revising your NCRT for chemistry. Whatever you have studied in chemistry, revise it from NCRT. You will surely get direct questions, especially in organic and organic chemistry. Direct questions are being asked nowadays from NCRT. So it becomes really important that you cover NCRT before going to any other material. Of course, you do your revision from all the sources that you have studied from, but do not neglect NCRT. And the other tip, keep solving questions. Question practice is always important in any competitive exams. Don't stress out. Okay. Have a good night's sleep. This is not the time to exhaust yourself. At least a week before exam, try to have a good sleep schedule. Do not take any kind of medications to induce sleep. Okay. Don't listen to anyone. These days they offer sleep medication which you take a day before or 2 days before. They'll tell you, but don't take any medications for sleep or relaxing yourself. Just start doing it. It's a natural process. It will take at least a week for you to get into a good schedule if you are not in a good schedule. So that will be my advice for you guys. JEE-Main is not that difficult. You just have to calm your nerves down and answer everything. Attempt all the questions. I would suggest if you're aiming for a rank. Otherwise, leave the questions you're not sure of. Don't go for negative marking. Okay. So yeah, that will be all, guys. Thank you very much. Goodbye.